Hello all, welcome to the next video of chemical kinetics. In this video, we'll cover order of reaction and molecularity. Let us see what is order of the reaction. Consider a reaction where A moles of A reacts with B moles of B to give C moles of C and D moles of D. The rate law for the above reaction is given as rate equals to K into molar concentration of A to the power X into molar concentration of the B to the power Y. Here X and Y represent the order with respect to the reactants A and B individually, and the sum of the powers of X and Y is called overall order of the reaction. In short, we can say X plus Y equal to order of the reaction. The sum of the powers of the concentration of the reactants in the rate law expression is called order of the chemical reaction. For a reaction, twice of hydrogen peroxide gives twice of water plus O2. The rate law is given as rate equals to K into molar concentration of H2O2. The reaction is of first order. Second example, the rate law for the reaction H2 plus I2 gives twice Hi. The rate is given as K into H2 I2. The reaction is of first order with respect to H2 and I2 each, and hence overall order of reaction equals to 1 plus 1 gives 2, and hence it is second order. Now let us study about the key points of order of the reaction. First, the order of a chemical reaction is experimentally determined. The order may be integral or fractional. For example, CH3CHO gives CH4 plus carbon monoxide. Rate equals to K into CH3CHO to the power 3 by 2. Hence, the order of the reaction is fractional, that is 3 by 2. Third, the order of reaction can be 0. For example, NO2 plus CO gives NO plus CO2. For this, rate equals to K into molar concentration of NO2 to the power 2. Order of reaction with respect to NO2 is 2, but with respect to CO is 0. It means that rate is independent of the concentration of carbon monoxide. Hence, overall order of reaction is 2. Fourth, only few third order reactions are known. Reactions with higher order than 3 are scanty. Now let us study about molecularity of elementary reactions. The complex reactions are those which constitute a series of elementary reactions. The molecularity of an elementary reaction is defined as the number of molecules taking part in the reaction. Elementary reactions can be defined as the reaction which takes place in a single step and cannot be broken down further into anything simple reactions. For example, ozone giving O2 plus O, ethyl iodide giving C2H4 plus Hi. These are the examples of elementary reactions. Now let us study about the molecularity of reactions. The molecularity refers to how many reactant molecules are involved in the reactions. Reactions involving only one reactant molecule are known as unimolecular reactions. Example: these are the two examples of unimolecular reactions where the only one reactant is involved in the reaction. Reactions which involves two reactant molecules are called as bimolecular reactions. For example, O3 plus O gives twice O2. In this reaction, two molecules are involved. Another example, twice NO2. Again, two molecules of NO2 are involved as a reactant to give the reaction. So these are the examples of bimolecular reactions. We have studied about order of reaction and molecularity of elementary reactions. Now, how order and molecularity of elementary reactions are related. Let's see. For this, consider an elementary reactions. For example, twice of NO2 giving twice NO plus O2. When we apply rate law, we can give rate equals to K into molar concentration of NO2 to the power 2. So here order of reaction is 2 and hence its molecularity is also 2. For another elementary reactions, C2H5I gives C2H4 plus Hi. The rate equals to K into molar concentration of C2H5I. It is unimolecular and first order. However, order and molecularity of the reaction may or may not be the same. Now let us study a rate determining step. From this picture, I would like to introduce the concept of what is meant by rate determining step. In this picture, there are two women working in a chocolate factory and the chocolate form are delivered on the counter. Now from here, there are three steps actually involved. Step 1, incoming chocolates, which is acting as a reactant. Step 2, wrapping of the chocolate, the process, and along with it, the side reaction which is going on is a consuming chocolate. And finally, the products, wrapped chocolates, are being formed. In the entire process, the number of chocolates wrapped or the product formed is based on the reaction at which the chocolates have been wrapped. In this case, it is the slowest step as compared to the incoming chocolates, and so the final product, the number of wrapped chocolates obtained, is dependent on the step 2. This shows that the slowest step is the rate determining step. With this example, let us now relate the same way to another example. For understanding rate determining step, complex reactions takes through a number of elementary steps, as we have seen in the case of a chocolate formation. One of these steps is slower than the other. The slowest step is the rate determining step. It also determines the rate of overall reaction. Let us see this example. twice of NO2Cl gives twice NO2 plus Cl2. This reaction actually takes place in two steps. First, NO2Cl gives NO2 plus Cl, and second, NO2Cl plus Cl gives NO2 plus Cl2. The first step is a slow step and second step is a fast step. And the overall reaction what we can write is twice of NO2Cl gives twice NO2 plus Cl2. First step being slower than the second, it is the rate determining step. The rate law is, for this, rate equals to K into molar concentration of NO2Cl. This also represents the rate of overall reaction. The reaction is of first order. In this reaction, Cl is formed and Cl which is being formed in the first step and is consumed in the second step. Such species represent the reaction intermediate. The concentration of the reaction intermediate does not appear in the rate law. Now let us study about the distinction between order and molecularity of a reaction. Here's a tabular form representing the differentiating point between an order of reaction and molecularity. First one, it is the sum of the powers of concentration of reactant in the rate law expression, whereas molecularity is the number of molecules of atoms taking part in an elementary reaction. Secondly, order is an experimentally determined value, whereas molecularity is a theoretical value. Thirdly, order depends on experimental condition. Molecularity does not depend on experimental condition. Order may be zero, fractional or integral. Molecularity is always an integral. It can never be zero or fractional. It gives idea about rate of reaction, does not give any idea about the rate of reaction. It is the property of both complex and elementary reactions. It is the property of only elementary reactions and has no meaning for the complex reaction in case of molecularity. With this, we complete the topic order of reaction and molecularity. Hope all of you have understood this concept. Thank you for watching the video.